Hello guys. Good morning. I'm audible. Can you hear me properly? I'm audible. Okay. I hope everything is all right. Please confirm. Good morning, Murli. Were you absent yesterday, Murli? Okay. So we have almost come to an end to our quantum mechanics course. After Born approximation, there may be one more class on relativistic quantum mechanics, and after that this will be over. So you keep on practicing problems because the theory part we have already covered. Is there any topic which is left, you can let me know, I will cover that. But I think I have covered the whole syllabus. If anything left, we can plan in the upcoming lectures. For the time being, we are almost at the end, and this is one of the most important topic which we are going to discuss today, Born approximation. This is part of the scattering chapter. Okay. Has the test resumed? Okay, Sunday test you are talking about, or which test you are talking about? We have launched test series. CSIR-NET test series is going on, and maybe by today or tomorrow, just test series will also come. So you can join CSIR-NET test series and give test, and Sunday test we are also going to resume. Test series for upcoming exam. Yes, for CSIR-NET exam we have launched. You can check it out. So Born approximation. You see, we talked about partial wave method. So the partial wave method, it was limited to the case of low energy scattering. Low energy scattering by a short range central potential. We have given you the assumption while discussing the partial wave method. It is applicable for low energy scattering by a short range central potential. Now, if the potential V of R is weak enough, remember this, weak enough, it will distort only slightly the incident wave. So it is like the wave is coming and your source of potential, so V of R, if it is weak, so what does this potential do? It will make some change in the incident wave. Now let's say the potential is weak, so it will have not much influence on the incident wave. So the incident wave will only slightly get disturbed. The first Born approximation consists then of approximating the scattered wave function psi r by a plane wave. What does it mean? Let's say you have a potential which is weak. V of R is weak. Now what will happen if you, let's say, send plane waves? So these plane waves will not get affected much because this potential is weak. So they will be just slightly get modified, and the scattered wave will also be plane wave. We have considered plane wave. Now the potential is weak, it will remain plane wave. The Born approximation is suitable for large and weak potential. Sometimes different combinations are given in 4 options. Low energy strong potential, large energy strong potential, or large energy weak potential. So you have to remember this one, that the Born approximation is suitable for large energies and weak potential, so that this plane wave does not get affected. So you can imagine, like, if you are very strong and in front of you some weak person is there, there will be no effect on you. Okay, or you can imagine it in this way. Other example, if I take like some strong animal, okay, strong animal passing a fence, the fence is very weak, So there will be no effect of the fence on the strong animal. The strong animal will easily pass through the fence. Getting my point? So large energy of the animal, you can see fence is weak, so weak potential. So you can imagine it in this way: large energy is weak potential. In that case, Born approximation is suitable. Partial wave method, low energy, short range, central potential. So sometimes statement based question can be framed from this. Now let us talk about this first Born approximation. So in the first Born approximation, we give the formula of scattering amplitude and differential scattering cross section. So if I take the help of the coordinate system, so let us draw the XYZ axis, X, Y, Z. So in scattering, what we have? Incident wave, scattered wave. Okay. So let's say we have this incident wave. So this is the incident direction and it gets scattered along some direction. So as you can see, if we denote the wave vector, let's say k0, this is the incident wave vector. Now scattered one will be k. So this is the original direction. So how much is the scattering? It gets scattered by an angle theta from its original direction. So this is how we define this scattering angle theta. So this picture we are redrawing here. Look, try to understand. This is k0 and this is k. So k0 can also be thought in this direction. So k0 and k, the angle between them is theta. If the angle between k0 and k is theta, half of this angle will be theta by 2 and theta by 2, right? So we are drawing it in this way. Let's say like this. So you can imagine it in this way, like this angle is theta by 2, this angle is theta by 2, this is k0 and this is k. Then in this scenario, if I consider, let's say, what will be this portion, this portion, what will be that portion? So it is like the resultant of these two vectors. So we define this resultant as Q. What is Q here? Q is nothing but the difference K0 minus K. So it is a triangular law of vector addition, you can imagine it in this way. So this Q is also written as chi. Magnitude of chi is Q. Q and chi, this is nothing but the magnitude of this K0 minus K. Okay. So if you have two vectors K0 and K, so Q, you can say K plus Q is equals to K0. So Q is equals to K0 minus K vector. So for this kind of case, what do you write? Square of it. So K0 square plus K square minus 2 K0 K cos theta. This one we have. Now this is only modulus, so there will be square root. Now you see, if you consider This is an elastic scattering. So in elastic, look, in the case of elastic scattering, in the case of elastic scattering, we know K naught incident wave vector will be equal to the scattered wave vector. K naught is equals to K, the magnitude. Okay, magnitude of K naught and K are same. So Q will become, you can see, let's say K naught is equals to K. So we can write K naught square. So K square plus K square, 2K square minus 2K square cos theta. And this is equals to what we can write. K square will come out as K 2 into 1 minus cos theta. 1 minus cos theta is 2 sin square theta. So 2 into 2, 4. So 2K sin square theta by 2. So 2K sin theta by 2. Is it clear? Look, Born approximation, this case we are discussing for high energy. For low energy also we will be giving you a formula. For the time being, let's focus on this high energy. So in fast Born approximation, we need to know about two things. One is the scattering amplitude. Scattering amplitude is given by this expression. The scattering amplitude is given by, so you need to remember this formula. Fk of theta phi, this is equals to minus twice m or mu is the mass, okay, by h cut square xi. Xi you got this 2k sin theta by 2 for elastic scattering. 0 to infinity r prime v of r prime sin xi r prime dr prime. Okay, so this is the formula, minus twice mu by h cut square xi, 0 to infinity r prime v of r prime sin xi r prime dr prime. So you have to remember this formula at any cost, and hence the differential scattering cross section, which will be the square of this scattering cross section, is then given by d sigma by d omega, which is the square of modulus square of the scattering amplitude Fk of theta phi mod square, and this becomes 4 mu square by h cut to the power 4 chi square modulus 0 to infinity v of r prime v of r prime sin xi r prime dr prime mod square. So you can just remember this scattering amplitude formula, and the differential scattering cross section will be determined by taking modulus of that square, modulus square. So from the theory perspective, this is what is important. Now we need to solve a lot of problems. Any question? Mu is the mass, okay? Additional formula, let me give you additional formula. h cut square k square by twice mu. Let's go for some problem. A free particle described by a plane wave and moving in the z direction undergoes scattering by potential V of r is equals to V naught if r less equals to r and 0 if r greater than r. If V naught is changed to 2 V naught keeping r fixed, then the differential scattering cross section in the Born approximation will be. No, mu is simple mass. Okay, sometimes it is denoted by mu and sometimes it is small m. So here you are given a free particle. Free particle is described by a plane wave moving in the positive direction, and it is perturbed. Undergoes a scattering by the potential this. Now if this value of V naught is changed to 2 V naught, then what will be the change in the differential scattering cross section? So you can see the differential scattering cross section depends on the applied potential V of r prime. Okay, so if you make it double, obviously you can see it will be quadrupled. You can easily see it from this. No, from Born approximation, we know f of theta 5 is equals to minus twice m by h cut square. Xi is also sometimes written as q. Okay. Zero to infinity r prime v of r prime. Okay, so here it is v of r sin kr prime sin kr dr. Okay, so we can write it minus twice m v naught by h cut square xi. When twice m v naught we can write if r less equals to capital R. So obviously the limit will be changed to 0 to capital R. So it will be r sin kr dr. So therefore the differential scattering cross section, differential scattering cross section d sigma by d omega, that is square of this scattering amplitude. So this is 4 m square v naught square by h cut to the power 4 xi square. Or simply, instead of writing this whole thing, you can simply just write twice m v naught by h cut square xi mod square, and it is 0 to r sin kr dr. Now you see this part has no dependency on v naught. Okay, so when v naught is changed to 2 v naught, we can write d sigma by d omega at 2 v naught will be equals to, you can see, twice m into 2 v naught by h cut square xi whole square, and everything other thing will remain same. Okay, so this will be equals to 4 times this whole thing. So 4 times d sigma by d omega for V naught. Okay. So increases to 4 times the original value. Option A. I hope this is very much clear. Let's go for the next problem. A particle is scattered by a central potential V of r is equals to V naught minus V naught r e to the power minus mu r, where V naught and mu are positive constants. If the momentum transfer, this Q is called momentum transfer. You can see K, and if you multiply h capital, that will give you momentum. So the difference, so this is incident momentum, this is you can say reflected or scattered momentum. So this Q is called momentum transfer. You can just name it, I forgot to mention it. This is known as momentum transfer. If the momentum transfer Q is such that Q is much greater than mu, the scattering cross section in Born approximation as Q tends to infinity depends on Q as. So you have to find out the dependency. Can you solve this problem, guys? This f of theta phi is also known as form factor. Okay? This has got another name, form factor. Okay. Look, f of theta phi we need to calculate first, then we'll just take the square, modulus square, then it will give you scattering cross section. So f of theta phi is equals to minus twice m by h cut square, xi is q here, okay, 0 to infinity, r prime, v of r prime, so v of r sin xi r prime, so sin q r dr, okay. So this is minus twice m by h cut square q 0 to infinity, v of r is equals to v naught r e to the power minus mu r. So r becomes r square, 1 r has been considered here, v naught e to the power minus mu r. Now sin q r, this one you can write as e to the power I q r minus e to the power minus I q r divided by 2i. So we have written it in terms of the exponential dr. So now it is the time to write. Look, this 2 and this 2 is getting cancelled, so we are left with m v naught by, let's say, h cut square q, 1 by I is minus I, so minus plus, zero to infinity r square, okay, e to the power minus mu minus IQ into R dr minus integration 0 to infinity R square e to the power minus mu plus IQ into R dr. Is it clear? So if you remember this formula, we have already given you many times. This formula has been used many times. So this was the formula 0 to infinity e to the power minus alpha x, x to the power n dx. This is equals to n factorial by alpha to the power n plus 1. This was the formula. So this is equals to m v naught I by h cut square q. What will be the first term? Here n equals to 2. So 2 factorial by alpha to the power n plus 1. So mu minus IQ whole cube minus here also 2 factorial divided by mu plus IQ whole cube. 2 taken outside, 2m v naught I by h cut square cube. This one mu square plus, let's keep it first, mu minus IQ cube mu plus IQ cube. This will be mu plus IQ minus mu minus IQ cube. Now you have to find out this. A cube minus B cube formula can you use? What is the formula of A cube minus B cube? A minus B, A square minus A square plus AB plus B square, na? So it will be similar. The effort needs to be shortened. Yeah, A plus B whole cube formula is there, but this is like A, this is like B. So A cube minus B cube. So the denominator part, mu minus IQ, mu plus IQ, is mu square plus Q square, right? Whole cube. Now let's apply this formula, A plus B whole cube. So mu cube A cube minus IK cube plus 3A square B minus 3AB square. Okay. A plus B whole cube, A cube plus B cube, 3A square B, 3AB square. Okay, this one we get from the first term. From the second term, we are forgetting the elementary formula, guys. A cube minus B cube minus 3A square B plus 3AB square. So it will be like this. So if you calculate, just do it by yourself. This is simple calculation. 6 mu square IQ. You see this mu cube, IQ cube, everything is getting cancelled maybe. IQ cube will remain. 2IQ cube or other things will get cancelled. Divided by mu square plus Q square to the power 3. We need to find out the dependency on Q only, along with the given condition that Q tends to infinity. Q much greater than mu. What does it mean? Q by mu is much greater than 1. Okay, or mu by q much less than 1, and for obvious reason mu square by q square will be much less than 1. So if I take I common, minus I common, then it will become plus. So this is equals to twice m v naught by h cut square q, 2 q cube minus 6 mu square q divided by mu square plus q square whole cube. Okay. So 1 q, if you take common, let's say q cube we are taking common. So it is proportional to, let's keep it twice m v naught by h cut square. Q cube we have taken common, q cube by q. So you are left with 2 minus, 2 we can also take common. So 1 minus 3 mu square by q square. Okay. Into 1 by, look here also we are taking q part, q square, so q to the power 6 mu square by q square plus 1 whole cube. Just check it whether we can write it or not. Yes, I think we can write it. So this is equals to 4 m v naught by h cut square. Let's write the dependence on q square. Here it is mu square by q square. You see it is approximately 0. We have seen it. So it is 1 minus 0 is 1. Okay, we can write it in this way, approximate. And this one mu square by q square is 0. So this is 1 by q to the power 6. So we can say this thing is proportional to 1 upon q to the power 4. So q to the power minus 4. So this is what we got. We got scattering amplitude. Therefore the scattering cross section cross section. So if you get too much excited in the examination, and if you see that one of the option is matching and you are not taking square, then it will be a mistake. The scattering cross section is sigma of theta phi, which is equals to f of theta phi mod square. So this is proportional to q to the power minus 4 square, so q to the power minus 8, and that's matching with option A. Let me know if it is clear or not. Can you move forward? Very similar problem I would like to give you here. Give it a try. The differential cross section, scattering cross section d sigma d omega for the central potential V of r equals to beta by r e to the power minus mu r, where beta and mu are positive constant, is calculated in the first Born approximation. Its dependence on the scattering angle theta is proportional to A is a constant. How to deal with this problem? Taking this final form is a bit challenging if we do not notice few things. Otherwise it is easy. So we will just apply the formula straightforward and see how we can get one of these answers. First of all, what is given? V of r is equals to beta by r e to the power minus mu r. So according to first Born approximation, what you can write? F of theta phi, this is equals to minus twice m by h cut square xi or q, whatever you write, 0 to infinity r prime v of r prime sin q r prime dr prime. Okay, so this can be written as minus twice m by h cut square q, 0 to infinity r prime is r here, v of r is beta by r e to the power minus mu r sin q r dr. Now the similar thing is going on, minus twice m beta by h cut square q, 0 to infinity r get cancelled, so e to the power minus mu r sin q r again e to the power I q r minus e to the power minus I q r divided by 2i. It's written like this. This is equals to minus twice m beta by twice h cut square q I. So it becomes minus minus plus, let's say, twice m beta I divided by h cut square q. Achha, let's remove this 2 as well. So m beta I by h cut square q. Now again we will be getting 0 to infinity e to the power minus mu minus I q r dr, 0 to infinity e to the power minus mu plus I q r dr. Okay, so this is getting easy as compared to the previous one. So beta mi by h cut square q, this is simple, e to the power minus mu minus I q r by minus mu minus I q, and here minus e to the power minus mu plus I q, क्या लिख रहा हूँ, e to the power minus mu plus I q times r divided by minus mu plus I q. Okay, acha, here we had minus, right? Limit between 0 to infinity. Let's put the value beta mi by h cut square q. So if you put infinity, then these two terms are 0. If you put 0, so minus minus plus 1 by mu minus iq plus minus 1 by mu plus iq. This is beta mi h cut square q. This is mu square plus q square, mu plus iq minus mu plus iq. You'll get it like this. This is equals to mu get cancelled, so 2 iq beta mi times 2 iq divided by h cut square q times mu square plus q square. So q get cancelled, so you are left with I square is minus 1, so minus 2 beta m by mu square plus q square. Okay. So did you miss anything? 2 beta m, h cut square is that. So this scattering amplitude you have got. Next, what you have to calculate, the scattering cross section, the differential scattering cross section, d sigma by d omega. Let me know if there is any mistake in the calculation. Okay, I have tried to make it as correct as possible. So square of this, so 4 beta square m square divided by mu square plus q square whole square h cut to the power 4. Is it okay? But the problem is the options are given in terms of sine theta by 2. So what you can do, you know the value of q. You know the value of q. Look, we have seen it before. If this was k, this was k naught, this was q. So q was for k naught is equals to k, we got q is equals to 2k sine theta by 2, right? So we'll put that q is equals to 2k sine theta by 2, and hence d sigma upon d omega, this is equals to 4 beta square m square divided by mu square plus 4 k square sine square theta by 2 whole square h cut to the power 4. Okay. Now if I take, by looking at the format, as you can see, it is proportional to sine square theta by 2 should be standalone. So if you want to keep sine square theta by 2 free, so 4k square should be taken common. Okay. So 4k square if you take common, then what it will come out as 16k to the power 4. Okay. Mu square by 4k square plus sine square theta by 2 whole square h cut to the power 4. So as you can see, this can be written in this form: 4 beta square m square divided by 4 k to the power 4 h cut to the power 4. Okay. And if I take this one, so mu square by 4k square plus sin square theta by 2 to the power minus 2. So this is proportional to, this is a proportionality constant. If I write it as a square plus sin square theta by 2 to the power minus 2, where a is equals to mu upon 2k. So I think now it is matching. So this extra thing you need to do to solve this problem. It came in part C, and the answer is also C. A square plus sin square theta by 2 to the power minus 2. Understood? It's a very beautiful problem. Now, few information I would like to give you. Any question from this? I hope everything is all right. Look, scattering of a particle of mass m from a hard sphere potential. Look, hard sphere potential, which is denoted by this V of r is equals to infinity for r less than a, and it is 0 for r greater than a. So you can imagine it like a sphere. Okay, inside it is hard, outside there is nothing, so it is 0. So for this case, total scattering cross section, so for hard sphere potential, remember hard sphere potential, total scattering cross section in the low energy limit will be written by sigma 0 is equals to 4 pi a square. Okay, and this is 4 times the classical value, 4 times the classical value of pi a square. Another thing to note down here is the total cross section for a black disk. The total cross section of the scattering from a black disk of high energies, it is written as 2 pi a square. Okay, high energy 2 pi a square, low energy 4 pi a square. Just remember these two things. One last thing here, we will be talking about the Born approximation for low energy limit. What will be, we have talked about first Born approximation is valid for high energies. So what will be the form of Born approximation for low energy? If in the question low energy is mentioned, then what formula are you going to use? The formula to be used is f of theta phi, this is equals to minus m by twice pi h cut square integration of v of r d3 r. This is the Born approximation for low energies. Minus m by twice pi h cut square integration v of r d cube r. So let us try to understand how to apply this in a problem. So a problem is given to you, a particle of mass m scattered with soft potential v of r, which is given as this. Low energy scattering amplitude, you have to find out the low energy scattering amplitude. F of theta phi is given by, look here, Born approximation is not mentioned, but low energy scattering amplitude we can find out from the Born approximation. That is why we are going to use that. So as simple as that, for low energy we know the formula. For the low energy, the scattering amplitude is given as you see f of theta phi minus m by twice pi h cut square integration v of r d3r. d3r is the volume element. This is equals to minus m by twice pi h cut square integration v of r is given to you, as you can see it is v naught for r less equals to a and it is 0 for r greater than a. So r 0 to a, limit will become 0 to a, so it is v naught d3r. d3r, you see this doesn't have any mention of whether it is in terms of r theta phi, or this is simple a constant. So d cube r can be written as r square dr sin theta d theta d phi. Okay, or simply we can just write there is no dependence on sin or no dependence on theta and phi, so we can simply write it is 4 pi r square dr. Okay, so this is equals to minus 4 pi m v naught. Acha, pi getting cancelled, so we are writing it. Acha, 2 is also cancelling. Many things are cancelled. 2 m v naught by h cut square 0 to a r square dr. Okay, so minus twice m v naught by h cut square r cube by 3 0 to a. So this is minus twice m v naught by h cut square a cube by 3. If I want to write it in the form of the given answer, it's nothing but minus 2/3 v naught m a cube by h cut square. That is matching with option B, right? One more problem we have, then we'll wrap up the session. Is it clear? Look at this problem. Consider the potential V of r is equals to V naught a cube delta cube r minus ri, where ri are the position vectors of the vertices of a cube of length a centered at the origin, and V naught is a constant. If V naught a square is much less than h cut square by m, the total scattering cross section in the low energy limit is. Look, a bond is not mentioned, but you can see low energy limit. From this we can guess that we have to apply the formula of Born approximation for low energy. So what is given to us? We are given V of r is equals to sum over I V naught a cube delta over 3 r minus ri. This is given to us. So this can be written as V naught a cube. This is three-dimensional Dirac delta function. So we can write delta of like x minus xi, y minus yi, z minus zi. Okay. This one we can write. What is x? What are these things? Xi, yi, zi. These are the coordinates of the vertices. Coordinates of the 8 corners at the vertices. Okay. Coordinates of the 8 corners of the cube. Whose center is at the origin. Okay. So in the low energy limit, f of theta phi, so you can write f of theta, phi dependence is not there, minus m by twice pi h cut square integration v of r d cube r. This is the formula, right? So this is minus m by 2 pi h cut square, v of r is v naught e cube. So now we have to take care of this integration. Sum over I equals to 8 corners, so 1 to 8. Okay, delta x minus xi, delta y minus yi, delta z minus zi into this d3r. In Cartesian coordinate it will be dx dy dz. Okay. And this is equals to minus m by twice pi h cut square v naught a cube. So if you put I is equals to 1, so x minus x1, y minus y1, z minus z1, dx dy dz. So this value will be 1. Okay. Next you put I equals to 2, then also you will get 1. So every time you will get 1. Eight times you will get 1. So this becomes minus 8 m v naught a cube by 2 pi h cut square minus 4 m v naught a cube pi h cut square. Okay, so this is the scattering amplitude. We need to find out the total scattering cross section. V naught a square is much less than h cut square by m. So the total scattering cross section what you have to find out. Let's look at the total scattering cross section. Total scattering cross section means it is talking about sigma, not differential. So first of all we need to calculate differential scattering cross section, then we'll go for total scattering cross section. Okay, so therefore the differential scattering cross section is given by d of theta. Let's say differential scattering cross section, which is f of theta mod square. So 16 m square v naught square a to the power 6 divided by pi square h cut to the power 4. Okay, therefore the total scattering cross section is, it is wait, we should write d sigma by d omega. Total scattering cross section is integration of d sigma by d omega times d omega. This is the formula, right? So this is integration 16 m square v naught square h cut to a to the power 6 pi square h cut to the power 4 d omega, sin theta d theta d phi. So if you take integration of this thing, this will give you 4 pi. Integration of d phi is 2 pi and integration of sin theta d theta 16 m square v naught square a to the power 6 by pi square h cut to the power 4 0 to pi sin theta d theta 0 to 2 pi d phi. Okay, so this part may not be visible. So sin theta to d theta is 2, d phi is 2 pi, so 4 pi, so 4 into 16 64. Look, have we made any mistake? Look, 64 a square divided by pi times m v naught a square divided by h cut square whole square. Can I write it? So that is matching with option C. 64 a square by pi m v naught a square by h cut square whole square. So option C is the correct option. Okay guys, it is clear. A to the power 6 we have kept a square outside and a to the power 4 we have taken inside by a square whole square. So with this we come to the end of this lecture. I hope you have found the session useful and easy. If you have any question you can ask, otherwise let's end the session here. Thank you very much. Have a great day.